Midnight. A soft hiss of static fills the headphones. Then, faintly, a human word seems to bloom out of the noise. Hello, is anyone there? For a heartbeat, your brain believes it. Your hand freezes on the volume knob. And even as the sound dissolves back into static, the question stays. If a real greeting arrived from the dark, where would it come from? And how would we know it was real? We like to picture a blinding beacon shouting across the galaxy. Reality is quieter. The first world-changing signal might be small and easy to doubt. It could sound like a whisper. It could resemble the countless transmissions we leak into space every second. Radio, television, radar, satellite chatter. So begin close to home. The closest hello may not be from anyone else at all. It might be our own voice coming back. When powerful radio waves strike the moon, a faint echo returns about 2.5 seconds later. Amateur operators call it moon bounce. The first time you hear your own signal return from the lunar surface, your mind insists someone else said it. That echo is a lesson. Space will happily fool you. But suppose it is not an echo. Suppose an unknown source calls out. Our nearest stars are only a few light-years away. Proxima Centauri sits a little more than 4 light-years from us. A simple, narrowband tone sent from one of its planets could reach our radio telescopes within a single presidential term. Teams at the Ceti Institute and Breakthrough Listen already point giant dishes at the nearest suns. Here is the catch. Space is noisy, and our own devices are noisier. Cell towers, satellites, even microwave ovens have fooled astronomers. A candidate once seemed to come from Proxima's direction and looked promising. After months of checks, it proved to be interference from earthly electronics. The disappointment stung, but it was necessary. False alarms teach rigor. They show us how hard honesty is under hope. So, what exactly would we listen for? Not a sentence in English, not a catchy melody. The most likely first contact is a pattern, a deliberate structure in the noise. It might be a steady tone that slowly drifts because the source is rotating or orbiting. It might be a repeating sequence of prime numbers, a mathematical handshake. It might be a narrow beacon that blinks on occasionally, like a lighthouse sweeping the sea. Verification is everything. A real signal should be seen by more than one telescope. It should track with the sky, not with our cell towers. It should show Doppler drift that fits a planet's rotation or orbit. It should survive tests where we point away and back again. It should be confirmed by independent teams using different hardware and software. That is how a whisper earns the right to be called a message. There is another uncomfortable truth. The first undeniable hello might already have washed over Earth before we had ears to hear it. Only in the last century have we built radio telescopes sensitive enough to catch a whisper from nearby stars. Even today, we listen to thin slices of the sky for thin slices of time. Imagine trying to learn a language by opening a dictionary at random once a year. If you were sending a hello, how would you do it? Would you leak it by accident, the way we do through entertainment and navigation and weather radars? Or would you build a beacon meant to be found? A beacon takes power and patience. It must run for years, maybe centuries. Many scientists suggest the water hole, a quiet part of the radio spectrum near natural hydrogen and hydroxyl lines, as a smart place to park a message. The closest meaningful signal might not be radio at all. Light can carry messages. Lasers can flash pulses so short they look like brief, bright stars. Observatories search for those optical pings. Others look for techno-signatures, signs of technology rather than messages. A strange chemical imbalance in an exoplanet's atmosphere. Nightside lights on a world that should be dark. Waste heat from engineering on a planetary scale. NASA now treats these as legitimate targets for search. Think of distance this way. 4 light-years is far to travel. Hearing from 4 light-years away is simply waiting 4 years after someone speaks. If a neighbor sent a greeting today, children starting 1st grade this fall could be finishing elementary school when it reached us. Meanwhile, Earth's radio bubble, the sphere of signals we have leaked for a little over a century, already stretches to more than 100 light-years in radius. Anyone inside that bubble has heard we are here. All of this returns to a human image, a person at midnight, listening. a world on the edge of a discovery it has hoped for since the first stories around fires. The first hello may be near. In practical terms, near like a long-distance call is near. You cannot touch it, but you can hear it. And once you hear it, you are not alone anymore. The hard part is less the hardware than the patience, the honesty, and the courage to be surprised. Here is our plan for this journey. In the chapters ahead, we will follow Earth's expanding radio bubble, map the nearest candidate stars, revisit famous false alarms like the wow signal, sit inside a modern control room, and test the physics of how far a whisper can travel. And then we will ask the hardest question of all. If a real hello arrives, what should we do next? For now, hold on to the first image, the hiss, the heartbeat, the word that may or may not be real. Hello, is anyone there? If the nearest signal exists, it is already on its way. When it arrives, our task is simple and enormous. Recognize it for what it is. The story of the nearest hello begins with the story of our own voice. For a little more than a century, Earth has been whispering into space without meaning to. At first, the whisper was clumsy and loud, spark-gap transmitters that splashed energy across wide bands, long-wave broadcasts riding the night ionosphere. Then came AM radio, shortwave, and the first television carriers. Those early analog TV signals had strong, steady tones that said, if you could place a giant dish around a nearby star and point it home, the carrier would look like a thin, bright needle in the noise. It was not eloquent, but it was easy to spot. Today our leakage is different. We stream instead of broadcast. Our towers are more efficient and point downward. The power per channel is lower, and the spectrum is chopped into many moving parts. Paradoxically, Earth has grown far more talkative for itself, and far harder to hear from a distance. The brightest accidental beacons we still make are radars. Airport radars, planetary radars, and military radars put serious power into the sky. When Arecibo Observatory was alive, its planetary radar had an effective radiated power that rivaled anything humanity ever produced in radio. That beam could light up an asteroid millions of miles away. If a nearby listener happened to sit inside the path of such a beam, they would not need to guess. They would see a deliberate, narrow, drifting tone that turned on and off with a schedule. Our other bright shouts are not aimed at the stars at all. The Deep Space Network, huge antennas at Goldstone, Madrid, and Canberra, sends tight beams to spacecraft at Mars, Jupiter, and beyond. Those transmissions are like laser pointers in radio form. They are incredibly strong in the direction they point, and invisible off to the side. If a hypothetical neighbor around Alpha Centauri sat in line with Earth and a Mars-bound probe during a transmission window, they could catch a needle-clean signal. If they were a few degrees off, they would hear nothing. It helps to picture the scale. At the speed of light, our earliest strong broadcasts now occupy a sphere roughly 100 light-years in radius. That bubble is not uniform. It is blotchy and thin. The first television carriers faded decades ago. Newer systems are more efficient and less leaky, but the bubble exists, and thousands of stars sit inside it. Some of those stars host planets we already know by name: Barnard's Star, Wolf 359, Tau Ceti, Epsilon Eridani, Proxima Centauri. The closest of all. If anyone there has been listening with the right kind of gear, they have already formed a first impression of us. Not from speeches or songs, but from the rhythms of our machines. Detectability is a harsh judge. Radio energy spreads out as the square of distance. Double the distance, and your signal's strength per square meter falls to a quarter. The universe also adds its own static thermal noise from the Milky Way, lightning on your own planet, hiss from the receivers. The way to win is not magic, but math. Narrow the signal to a tiny slice of bandwidth so the noise in that slice drops. Integrate over time so random noise averages out and structure remains. Correct for Doppler drift, because the source and the listener are both rotating and orbiting. These are the everyday tools of radio astronomers. They are the reason a civilization with technology only centuries ahead of ours could pick out our radars across many light years. while a civilization at our level might only hear us from the next neighborhood over. Sometimes our own tools confuse us. A few years ago, a narrowband signal that seemed to come from Proxima's direction set hearts racing. It had the kind of frequency drift you would expect from a transmitter on a spinning planet. After months of study, the team traced it to terrestrial electronics. The disappointment was real, but so was the lesson. Space is generous with lookalikes. Even nature plays tricks. Fast radio bursts are brilliant flashes that last milliseconds, coming from distant galaxies. They are now understood to be astrophysical, but for a while they sat on the border of mystery. Earlier still, a set of periton signals at a famous dish turned out to be microwave ovens opening mid-cycle. When you look for wonder, the first thing you find is how many ordinary things pretend to be it. There is also a difference between leakage and beacons. Leakage is a city seen from far away at night. It is scattered and variable. It tells you something is alive, but not what it wants to say. A beacon is a lighthouse. It costs energy to run and discipline to maintain, and it carries intent. The Arecibo message of 1974 was an intentional shout toward the star cluster M13. It was mostly ceremonial. The cluster is 25,000 light-years away, and by the time the message reaches those stars, their positions will have shifted. But the point was to show what a deliberate, structured transmission looks like. If we ever choose to speak again, the physics is ready. The nearest stars would hear us within a human lifetime. Optical beacons are in the same family. A powerful laser firing nanosecond pulses would look like a brief, bright star to a distant telescope. They sit alongside hunts for technosignatures, unusual chemistry in an atmosphere that sunlight cannot explain, night-side brightness that winks like a grid of cities, waste heat spilling from a world as if great engines were working there. NASA and the national academies now talk about these ideas in sober terms. The category has moved from playful to professional. So what counts as the closest signal that could plausibly say hello? The honest answer is twofold. The closest signal we can check any night is our own echo moon bounce, satellite scatter, a radar ping that left home and came back. The closest signal that could be real from someone else would come from the nearest handful of stars. A focused transmission from a planet around Proxima, Alpha Centauri A or B, Barnard's star, or Tau Ceti would be strong enough for our best instruments. It would look like an impossibly clean line in the noise with a living, physical drift. It would be there when one observatory pointed, and be there again when a second observatory, half a world away, checked. And it would carry a deeper meaning. If a neighbor chose to send a beacon, it would mean they decided the cost was worth it. It would mean they expected not just to be heard, but to be understood. We should not assume that. We might be surrounded by cautious listeners who prefer to watch rather than speak. We might be early, alone in a quiet neighborhood, waiting for the next city to turn on its lights. Or we might already be the loudest thing for 10 light-years and simply have not noticed how obvious we seem. In the next part, we will draw a map of those nearby suns, look at the telescopes that watch them, Green Bank, Murray-Young, Meerkat, FAST, and explain how a modern search scans huge swaths of frequency without blinking. We will also ask a personal question. If strangers close by have been listening, what version of us have they heard first? Picture a neighborhood map pinned with small lights. Each pin is a nearby sun, close enough that a hello could cross the gap within a human lifetime. Closest are the Centauri stars, Alpha Centauri A and B, plus tiny Proxima. A step beyond sits Barnard's star about 6 light-years away, then Wolf 359, Lalande 21,185, and the bright outlier, Sirius. Epsilon Eridani and Tau Ceti anchor the next ring, close, steady, and long-watched. Now imagine our listening posts aimed along those lines. In West Virginia, the Green Bank Telescope, 100 meters of quiet steel, listens from a protected valley. In Australia, Murray-Young, the park's dish, turns its ear beneath a Milky Way that looks like smoke. In South Africa, the Meerkat array weaves dozens of dishes into one giant eye. And in Guizhou, China, the fast dish 500 meters across leans toward the forest and hears whispers others miss. Together they can sweep the nearest stars and come back later to see if anything stayed. How does a modern search work? Think of the radio dial as an ocean. Engineers slice it into billions of narrow channels measured in hertz, so a single steady tone can stand out. Software corrects for Doppler drift as worlds spin and orbit, and it stacks faint repetitions so randomness cancels and structure remains. At the same time, it flags trouble, tones that appear in every direction, bursts that match a satellite pass, patterns known to come from our own machines. Cadence keeps us honest. Observers run on-off sequences, point at the star, step aside, point back. Others piggyback on ordinary astronomy. While a telescope maps a nebula or times a pulsar, a second computer quietly searches the same data for needles that do not belong to nature. This commensal strategy turns routine hours into a continuous vigil. Data rates are huge, so pipelines triage candidates and surface a few for human eyes. The classic view is a waterfall plot, frequency versus time, where a real signal draws a hair-thin drifting line. Fakes blink, smear, or sit glued to one exact frequency no matter where the dish points. Veteran listeners learn the fingerprints of planes, satellites, and ground gear the way sailors learn coasts. Machine learning helps but never replaces judgment. If a candidate survives the first filter, the next step is independent confirmation. Call another observatory. Share the coordinates and the tune. If both teams see the same tone with the right drift, confidence climbs. The gold standard is a repeat on a later night from the same place in the sky. Which neighbors do we favor? Sun-like stars are familiar and stable. Red dwarfs are common and often host rocky worlds close enough to warm. Proxima likely has a small world in a snug orbit. Barnard's star shows hints of a colder, heavier planet. Tau's Ceti may carry several small worlds. Epsilon Eridani wears a broad dust belt that hints at planet building. Each pushes its pin a little brighter on the map. What would they hear from us? Not speeches, but machinery. Early on, it was the steady hum of analog carriers, the grease pencil heartbeat of radar sweeps, Morse and teletype, the chirp of modems. Later, it became bursts and packets, timing pings, and the razor-thin whoosh of deep space transmissions to probes that light up for an hour and vanish for a day. From a few light years away, Earth would look like a busy harbor. Because we listen more than we speak, precision matters. Arrays like Meerkat can form multiple beams, tiling a patch of sky like facets on an insect eye. Multi-beam receivers on single dishes do the same. If a tone appears in only one beam, while the others stay quiet, confidence rises. If it splashes across them all, you are probably staring at your own equipment. All of this funnels toward one prize, the nearest unambiguous artificial line in the sky. Narrow, drifting as physics demands, present when we look and gone when we look away. Seen from more than one place on Earth, and, best of all, seen again. Nearest means the round trip for a reply is imaginable to a person, not just to a civilization. A few dozen suns live inside that conversational distance, and if nothing answers, the map still matters. Each null result is a contour on our chart of the quiet guiding future listeners toward better ideas. Different frequencies, different kinds of light, even different messengers such as neutrinos or gravitational waves. The search grows wiser the longer it fails, and the neighborhood grows less mysterious. Start by imagining the shape of a real hello, not a sentence, but a spine. A true artificial signal has bones you can measure. First, it is narrow, so narrow that on a frequency plot, it looks like a hair laid across a page. Nature paints broad strokes. Lightning, nebulae, and hot gas smear their power over wide bands. Technology squeezes energy into a tight slice because efficiency and intention demand it. Second, the line drifts. It slides at a steady rate because the sender and the listener are both spinning and orbiting. That Doppler drift is not a flaw, it is a fingerprint. The famous near miss that shows how such a moment might feel arrived in 1977. The Big Ear radio telescope in Ohio caught a narrow, strong burst near the hydrogen line. It lasted 72 seconds, the time it took the sky to drift across the telescope's beam, and then it was gone. Astronomer Jerry Amon circled the printout and wrote, "Wow," in the margin. No one has proved it artificial. No one has proved it natural. It lives where many candidates live, the valley between maybe and probably not, a reminder that a single flash is a poor witness. Modern searches try to earn a firmer ending. They build redundancy into the very first minutes. Point on, step off, point on again. If the tone fades when you look aside and returns when you look back, confidence climbs. Call another dish half a world away. If both see the same line with the same drift, then check polarization the way the wave's electric field swings. Many human transmitters choose a polarization for practical reasons. A natural source can be polarized too, but a stable man-made preference is one more clue. Distance complicates everything, and that is where nearest becomes your ally. The interstellar medium is not empty. It is a thin ocean of charged particles that can smear and scatter a pulse. Over thousands of light years, bright flashes fog and sharp edges round off. Over a few light years, your message stays crisp. That is why the first believable hello is far more likely to arrive from the nearest stars than from the far side of the galaxy. Physics gives close neighbors a clarity advantage. The same physics guides where to listen. There is a natural quiet zone in the radio spectrum between the hydrogen line at 1420 MHz and the hydroxyl line around 1667 MHz. Astronomers jokingly call it the water hole because H plus OH makes H2O. It is quiet because nature keeps it clean and because transmitter use there is limited. A beacon placed there would stand out, and we already watch that band with care. But smart strategies also roam. Higher frequencies for tighter beams, lower ones for bigger reach. Optical pulses for laser-like flashes that look like brief stars. False alarms will keep coming. Years ago, a set of mysterious pulses at a famous dish turned out to be microwave ovens opening mid-cycle. More recently, an intriguing narrowband candidate from Proxima's direction became hardware interference after audit. You could call these embarrassments. Better to call them training. Every eliminated candidate strengthens the filters and teaches the community how to avoid fooling itself. Science is not a staircase. It is a ramp sanded smooth by failures. Suppose then that a tone survives the gauntlet. What happens next? The rule is simple. Publish the data. Independent teams attempt to confirm. Teams across the world point antennas. If the source repeats, you record as much as possible with the widest practical bandwidth, because a beacon might hide a slower message underneath. You also rotate through receivers, backends, and software chains, because a real hello should not vanish when you swap tools. How would you decode a first layer? Start modestly. Look for patterns that do not depend on culture. Prime numbers, binary grids, geometric sequences. The Arecibo message of 1974 used a 1679-bit image because 1679 factors into 23 by 73 in exactly 2 ways, inviting a receiver to lay the bits into a rectangle and see a picture. A real sender might do something similar, but more robust. Redundant formats, checksums, a slow header that teaches a tiny alphabet first. This is less science fiction than engineering empathy, designing for a listener who shares physics, but not history. Could the nearest hello come not from a star, but from inside our own backyard? Some researchers argue we should also search for lurkers, old probes parked in Earth-Moon stable orbits on the far side of the Moon, or co-orbiting with Earth. If such an object woke occasionally and pinged a tight beam toward our surface, detection would feel like hearing a whisper from across the street rather than across town. It is a minority idea, but it is testable with radar surveys, optical sweeps, and radio watches of the Lagrange points and the lunar far side. All of this might sound abstract until you picture the control room at 2 a.m. Someone watches a waterfall display where noise looks like rainy glass. A line appears. It moves with the sky. It holds steady when the dish turns back. It is not on the satellite list. The operator calls a colleague in another hemisphere who is just starting their morning. Minutes later, a second waterfall shows the same hairline drift. If this ever happens and survives the next hour, that hour will be documented like no hour before. Near, then, is not only a map distance but a human one. Near means you can ask a question and dare to hope you might live to hear the answer. It means physics is kinder, verification is cleaner, decoding is more plausible, and patience has a fair chance of being rewarded. The universe is very large. Our neighborhood is not. If a first hello exists, the smart money says it comes from here. Next, we walk that neighborhood star by star and meet the world's most likely to speak or to listen. Let's walk the neighborhood star by star and ask a simple, practical question at each door. If someone there wanted to say hello, what would we likely detect, and how soon could we hear it? Proxima Centauri comes first. A cool red dwarf, a little over 4 light-years away. It is small, temperamental, and close enough that our instruments revisit it often. Proxima b, roughly Earth-sized, circles every 11 days and probably keeps one face to the star, leaving a band of permanent twilight around the terminator where mild climates could persist. Proxima's frequent flares bathe the system in bursts of radiation that might stress biology, but also make radio weather lively. A transmitter on Proxima b or in high orbit would most likely place a razor-thin tone in the quiet water hole of the spectrum and let Doppler drift right a graceful slope as the planet spins. From here, the line would look fragile at first, and then grow undeniable as repeated passes stack up. Next door are Alpha Centauri A and B, a warm, bright pair much like our Sun. No small, temperate world has been confirmed there yet, but the system is a verifier's dream because it is bright, accessible, and watched from both hemispheres. A deliberate beacon from either star would look like textbook intent, a hair-fine line, steady cadence, clean on-off tests, and a Doppler curve that slowly evolves over months as the binary orbits. That long-term, clockwork bend would be a living signature, a reminder that the sender's sky is moving in a way only physics could choreograph. Barnard's star sits about 6 light-years away. It is old and quiet, and slides across our sky faster than any other bright neighbor, a reminder that stars are cities in motion, not fixed beacons. A cold, heavy planet was once reported there and later questioned, so Barnard's remains a tantalizing maybe. Yet age cuts both ways. An ancient system could host builders who learned thrift long ago. Instead of a power-hungry broadcast, imagine a pencil-thin beacon that lights for 2 minutes at the same local sidereal time each night. Detecting it would mean discipline on our side. Point at the same clock tick, stack the frames, correct for drift, and let the noise average down until a line appears where nature has no reason to draw one. Wolf 359, roughly 8 light-years distant, is a dim red flare star, a neighborhood of radio storms. Flares shove energy into space across wide bands and can masquerade as purpose if you squint. That is why repetition and polarization matter. A machine-made tone keeps its shape through the weather. It drifts with orbital mechanics, not with tantrums. If you can prove artificial structure against a background this rowdy, you can prove it anywhere. A verified line from Wolf 359 would be like hearing a violin hold a note steady in a wind tunnel. Epsilon Eridani, about 10.5 light-years away, is a youthful K-type star with a broad dust belt and at least one giant planet farther out. Dust means leftovers from building worlds. It also means collisions that stir the system. For listeners, mess can help. Dust and gas carve windows where nature is quiet, letting an engineered tone stand out. A steady signal here would likely be narrowband and modest in power, but its Doppler drift would obey the same clean arithmetic, daily rotation laid over an orbital year, a rhythm that no satellite list on Earth can mimic when multiple observatories see it independently. Tau Ceti, at roughly 12 light-years, looks like a calmer cousin of our Sun, and has long worn the daydream crown for nearby mature system. Astronomers see signs of multiple small planets and a heavy debris disk. Heavy debris means more impacts tough on young biology, but hardly a barrier to a patient technologist. If someone there preferred radio quietness, an optical beacon might be their hello. Brief laser flashes encoding a simple mathematical handshake, primes, binary grids, geometric sequences timed to repeat with reassuring stubbornness. To us, those flashes would look like tiny, punctual stars that wink and return on schedule. Distance is only half the story. Geometry changes the odds as much as biology. Some stars sit in the Earth transit zone, the narrow strip of sky from which our planet would be seen crossing the Sun. From those desks in the cosmic classroom, Earth betrays its air, its seasons, and the hint of oceans. A star with that vantage has motive to point a beacon our way. Nearby systems drift into and out of this strip over millennia. When they are in class, their priority rises on every nightly schedule because a curious neighbor there would already know Earth is interesting. Now fold in time. A one-way hello from Alpha Centauri takes a little over 4 years. From Barnard's star, about 6. From Epsilon Eridani and Tau Ceti, roughly 11 and 12. A conversation that asks and answers even once demands 8 to 25 years of patience. That sounds long until you compare it to the age of cities and languages. For a species that builds cathedrals and archives, a dozen winters is a manageable wait and a thrilling one if a reply date can be circled on a calendar. So what should we schedule on our side? You do not stare at one pin forever. You rotate. Build a cadence. Alpha Centauri at dusk, Proxima near midnight. Barnard's star before dawn, then repeat tomorrow, next month, next year. Add optical watches for laser pinpricks. Coordinate with teams on other continents so a candidate can be checked immediately. Record raw voltages when something looks promising so nothing subtle is lost in processing. And keep a short, nearest list that receives extra attention. Because proximity makes physics kinder, verification cleaner, and decisions faster. A neighborhood tour ends with a feeling more than a fact. The odds that any one pin is speaking today may be small, but there are many pins, and time is long. The near sky is where patience pays first. The verification is simpler, the waiting is humanly bearable. Nearest does not mean guaranteed, it means possible in a way a life can hold. That is enough to keep the headphones on and the schedule full. Next, we move from star charts to checklists and write the practical, unforgiving steps that turn a curious tone into a claim the whole community can test. Turn a curious tone into a claim you can defend. And you have a roadmap that anyone can audit. The first minutes matter most. Write down everything, exact time in coordinated universal time, where the telescope was pointing, the frequency and its tiny drift per second, how narrow the line is, how strong it is above the background, and whether it appears in one polarization or both. Then, run the simplest, most powerful test in radio astronomy. On, point at the source, step aside, point back. Real signals track the sky. Interference sticks to the ground. Next, change something. Rotate the feed to swap polarization, nudge the focus, switch to a different backend or a different digitizer. A genuine line should survive equipment shuffles. If the tone vanishes when you change gear, it probably lives in your gear. Meanwhile, log the radio environment around you. Many observatories keep local fingerprint lists frequencies from aircraft beacons, satellites, and nearby transmitters. If your candidate matches a known culprit, stop the celebration and start the paperwork. If it passes those hurdles, call a friend, preferably far away. The single best antidote to fooling yourself is geography. Another dish under another sky with another electrical diet either sees the same hairline drift at the same sky position, or it does not. Ask them to record raw voltages if they can. Baseband captures preserve the full electric field through time, so later you can rechannelize, research for drift, and test alternate decoders without losing any nuance. Timestamp everything with disciplined clocks. GPS-disciplined oscillators are the standard heartbeat. Software runs a parallel race with the hardware. Narrow channels carve the spectrum into thousands or millions of tiny lanes, so a single car signal is obvious. Algorithms search a grid of drift rates to line up the lane with the way an orbiting, rotating transmitter should slide. Integrating over time lets randomness cancel while structure holds. Interference, excision tools look for telltale fingerprints, signals that are present in all directions at once, lines that repeat at exact power grid harmonics, bursts that match satellite passes to the minute. The aim is not to be clever, it is to be boringly thorough, because a claim strong enough to change textbooks must survive boring tests. Bias is the enemy inside the room. Build procedures that make excitement less dangerous. Some teams run blind injections, fake signals slipped into pipelines without warning to keep reflexes sharp, and check that no one leans on a single plot or a single person's judgment. Others require that a junior member lead the early audit, precisely because they are not invested in winning a headline. The tone of the logbook matters. Describe, don't conclude. Narrow line with drift consistent with low Earth satellite is better than alien maybe. Suppose the line is still alive after hours of skepticism. What then? Transparency. Publish what you have, quickly and responsibly. That means releasing raw or near raw data in standard formats, plus the tools you use to read them. It means writing methods in plain language so another team can replicate the steps. A short preprint can say a lot without saying too much. Here is where and when. Here is the drift and bandwidth. Here are the on-off-on tests. Here is the independent look. Here is what we ruled out. Here is what we cannot yet rule out. Resist the urge to tell a story bigger than the evidence. Let the community try to break your result. If it bends, you just saved everyone time. If it does not, confidence grows. Underneath the carrier, there may be cargo. A pure tone can hide information by changing its phase or its frequency in tiny steps. Sidebands, little symmetries around the main line can betray a slow data rhythm. If you suspect content, proceed like a cautious cryptanalyst rather than a treasure hunter. Start with universals, prime counts, binary blocks, simple checksums, repeated frames that suggest headers. Assume redundancy and error correction. Because engineers everywhere hate data loss, expect a preface that teaches the alphabet before the poem. And keep the decoding work offline. There is no plausible way a radio file can infect a telescope, but isolating the analysis avoids even the appearance of recklessness. Now comes the social gravity. For decades, scientists have drafted and debated post-detection guidelines. They are not laws, but they sketch a norm. Verify first, inform widely, share data, avoid any transmission on behalf of Earth until there is broad international consultation. The last point is contentious. Messaging the stars pressing reply is a separate ethical problem that this checklist does not need to solve on night one. The nearest hello does not automatically demand an answer. It demands care. Inside your own team, plan for the human wave. Phones will light up. Reporters will call. Appoint a calm, factual voice who can say what is known and what is not without adding drama. Keep an internal red team of people whose job is to kill the result if they can. If they fail honestly, their failure becomes part of your confidence. If they succeed, their success becomes part of your education. Drills help more than pep talks. Practice on known targets. Use a spacecraft in deep space as an artificial star. Track a probe headed for Mars, and let the pipeline treat it like a mystery. Time the Doppler curve as Earth rotates. Prove that two observatories can hand off a candidate in minutes rather than days. Run a tabletop exercise where a false positive makes it all the way to the director's desk and then gets caught. Every stumble in rehearsal is a smoother step in the real thing. Timescales are a gift and a trap. You have minutes to run on, off on, and call a second dish. Hours to attempt a repeat. Days to write a careful note. Weeks to let others weigh in. The temptation will be to name the experience before the evidence is complete. Do not. The only thing worse than missing a historic hello is teaching the world not to trust you when the real one arrives. Safety is not just about equipment. A true nearby hello will spill into culture. Rumors will outpace facts. Expect copycats. Expect hoaxes. Expect deepfakes of your control room. That is why data releases and independent confirmations are not just scientific hygiene, they are public service. When people can check you, they do not have to trust you. Put all of this together, and nearest becomes more than a distance. It becomes a philosophy of readiness. Keep a short list of nearby targets and a short list of partner observatories. Keep a public page that explains your protocols in plain language. Keep your tools boring, your logs meticulous, your claims modest, and your doors open. You are not just preparing to hear a word. You are preparing to be believed when you report it. One day, a thin line will pass every test you can throw at it and keep standing. When that day comes, the difference between a myth and a message will be the homework you did beforehand. The checklist will not make the moment less wondrous. It will make it real. How far can a whisper travel? Strip away the romance and first contact becomes a link budget problem. Energy in, losses along the way, and sensitivity at the ear. Space takes its cut with the square of distance, double the range, and your signal spreads over 4 times the area. The rest is craft. Put power in a tight beam. Keep the message narrow, listen a long time, and use an ear that wastes none of the arriving energy. Start with beams. A flashlight seems brighter than a candle, not because it makes more light, but because it aims it. Radio dishes work the same way. A modest transmitter feeding a precise antenna can produce an effective radiated power far beyond the raw wattage of the amplifier. On the receiving side, a big dish is a big cup. It gathers more of the rain. If 2 neighbors trade narrow beams, the universe suddenly feels smaller. Across a few light years, a football field-scale dish listening for a razor-thin tone from a comparable dish is not a fantasy. It is a practical conversation, measured in hertz and hours. Bandwidth is the quiet tax. Noise lives everywhere, but you only pay the noise that leaks into the slice of spectrum you watch. Squeeze your message into 1 hertz, and you compete with 1 hertz of hiss. Widen the channel, and the noise bill rises in step. That is why the archetypal beacon is a slender, unwavering line. It is not poetry, it is accounting. Narrow allows faint, and faint allows far. Time is the second accountant. Random noise wanders. Signals persist, seconds into minutes and minutes into hours, and noise tends to cancel, while any stable pattern adds up. That is integration. And it is the superpower of patient listeners. Meter by meter, second by second, the universe gives patience a discount. Frequency stability is the spine that makes patience work. On both ends of the link, you need clocks that do not slide around. Hydrogen maser and rubidium standards keep modern receivers anchored, so a 1 Hz lane stays a 1 Hz lane all night. Software then corrects the slow drift caused by rotation and orbits, effectively holding the lane still while the sky moves. With that trick, a whisper earns the right to be averaged thousands, even millions of times. The medium between the stars is thin, but not nothing. At radio frequencies around a few gigahertz, interstellar gas barely smudges a narrow line over a few light years. At lower frequencies, charged particles can scatter and delay pulses. At higher ones, beams become pencil-thin and demand cleaner pointing and steadier oscillators. None of these effects are showstoppers at neighborhood distances. In truth, the hardest medium is the one under our feet, our own radio soup of satellites, aircraft, towers, and gadgets. That is why true tests move the dish on and off target, change polarization, swap receivers, and call a second observatory far away. The sky should carry the tone. The ground should not. A thought experiment puts numbers into feelings. Imagine a cautious civilization around a nearby red dwarf. Instead of running a cathedral-class transmitter, they use a modest station with a high-quality dish, firing a narrowband beacon for 10 minutes at the same sidereal time each night. Their beam is tight, their tone is stable, Here on Earth, a large dish aims at that star for a month of such windows and stacks the data. Each night's look adds a faint pencil stroke to the same spot on the page. Night after night, the hairline grows darker until even a skeptic sees it. Nothing magical changed at the transmitter. We simply let time do what power could not. Optical beacons play the same economics with photons instead of volts. A laser can dump a burst of light in a billionth of a second. To a distant telescope, that looks like a star that blinked once, and then, an hour later, blinked again at the same color and the same tick of the sender's clock. The trick is pattern and persistence. Random twinkles from the atmosphere are messy. A disciplined, repeating wink is a signature. In the optical, the beam versus candle advantage is even larger. A meter-class transmitter and a meter-class receiver can trade extremely tight beams across many light-years if both sides keep time and point well. Coherence time, how long a signal stays phase-true, is a quiet hero. Many efficient encodings ride on predictable phase, but the interstellar medium, transmitter instabilities, and receiver noise conspire to fray that predictability. Nearby links have long coherence times, which means smarter encodings survive. That in turn allows more information to be tucked under a modest carrier without losing detectability. If the first hello carries cargo, say, a short header teaching a numeric alphabet, neighborhood distances are where that header stands the best chance of arriving intact. None of this means brute force is useless. A lighthouse helps ships even on a calm sea. A powerful beacon from a nearby system would be unmistakable. But the link budget view highlights something more democratic. Near lets ordinary tools win if they are used with uncommon care. You do not need continent-spanning arrays and nation-sized power plants to be heard across 5 or 10 light-years. You need good oscillators, clean antennas, smart software, and a calendar. Leakage, by contrast, is sloppy messaging. Our radars and deep space links are bright in their lanes, but they were not built for neighbors. Their beams sweep, hop, and shut off. Their cadences serve weather, air traffic, and probes. From a nearby star, a listener might puzzle out our habits, the way you can infer a city's shift changes from the pattern of lights in office towers. That is contact of a sort, accidental anthropology. A true hello would replace inference with intention, a line placed where nature is quiet, repeated with stubborn discipline, and shaped by the clean drift of orbital mechanics rather than the schedules of airplanes and satellites. Let's add geometry. The sky is not a static dome. It is choreography. Earth's spin adds a daily Doppler wiggle. Earth's orbit adds a yearly one. The sender's world does the same. Stack those together and you get a slow dance in frequency that is predictable to anyone who can measure. A real beacon will ride that dance exactly. That is why nearest helps so much. The steps are small and clean over a few light years, and we can model them precisely. Across thousands of light years, the dance is muddied by scattering, scintillation, and long, slow drifts in interstellar weather. Finally, consider energy ethics. Broadcasting loudly in all directions wastes power. Broadcasting tightly to a short list of likely listeners conserves it. Who are the likely? Stars with planets in comfortable orbits. Stars in the Earth transit zone, where our world would be seen crossing the sun. Stars that have been quiet and steady for billions of years. A neighbor who values thrift will aim, schedule, and repeat. To meet them halfway, we should do the same. Keep our nearest list, keep our optics and radios disciplined, and keep our ears open more nights than we think we need. Seen this way, the romance does not fade, it clarifies. The nearest hello is not a miracle. It is an engineering match between two cautious civilizations who share physics and patience. The distance is large, but the rules are on our side. Narrow beats wide. Time beats noise. Beams beat candles. Clocks beat drift. And neighbors beat strangers because the universe is kinder at short range. If a first hello happens in our lifetimes, it will almost certainly be a small thing done with great care. An ordinary line in the noise that, once recognized, becomes the most extraordinary sentence we have ever heard. Next, We step from the economics of the link to the psychology of the listener, how humans hear patterns in noise, why our brains love false alarms, and how to design a search that stays honest when hope gets loud. Begin with the brain. Before we built dishes and laser detectors, evolution built a pattern finder inside our skulls. It kept our ancestors alive. Hear a rustle, imagine a predator, act fast. The same gift now sits in a control room at 2 a.m., staring at a waterfall plot. The brain would rather invent a tiger than miss one. In radio astronomy, that impulse turns noise into whispers and coincidences into intent. Psychologists call it apophenia, when we see structure in randomness, and pareidolia, when formlessness becomes a face. We hear words in static, rhythms in air conditioner hum, meaning in a hair-thin line. Hope raises the volume. After months of null results, any crisp feature seems to ask for a story. Confirmation bias then arranges the evidence. We overweight data that fits our hunch and discount the rest. In a huge parameter space, millions of frequency bins, thousands of drift rates, many time windows, the Texas sharpshooter fallacy waits. Shoot the barn, draw a bullseye around the tightest cluster, and call it a hit. If you poke long enough, chance will sketch a suspicious line somewhere. The garden of forking paths makes it worse. Try many analyses. Remember the one that worked. Add expectancy effects. If the schedule says Proxima at 3:14, hiss from that direction feels nobler than hiss at 3:27. If a colleague says, I see it, you are likelier to see it too. Fatigue bends thresholds. The difference between real and probably not can be a cup of coffee. Hence procedures over stories. Build searches like clinical trials. Predefine bands, drift rate grids, and promotion statistics. Choose a false alarm rate in advance and stick to it. Keep a holdout set for final checks, so you don't train your eyes on the same noise you are trying to reject. Write logs in plain language. Describe first, interpret later. Blindness helps. Inject synthetic signals that look real without telling operators when they appear. A pipeline that cannot catch a fake will not reliably vet the real thing. Blind injections also humble the room. They remind veterans that judgment can be fooled and reassure newcomers that caution outranks drama. When a true candidate appears, reflexes are ready. Run on, off, on. Call the partner dish. Capture voltages. Swap hardware. Repeat. Culture is a safety system. Assign a designated skeptic for each run, someone whose job is to ask boring questions until answers stop wobbling. Rotate that role so it carries prestige, not stigma. Celebrate falsifications. A microwave oven periton that dies under audit is rehearsal, not failure. Publish postmortems so new students inherit scars without earning them the hard way. Statistics give discipline teeth. Set thresholds by measured noise distributions, not by hunch. Define a signal-to-noise requirement and a drift coherence metric. Use out-of-sample confirmation and, when searching many bins, correct for multiple comparisons. False discovery control is unglamorous, but it keeps a once-a-decade headline from becoming a once-a-week apology. Remember famous temptations. A one-off burst in 1977 earned exclamation marks, but no repeat. Decades later, a tidy, narrow line near Proxima's direction stirred hopes until audits traced it to earthly hardware. Fast radio bursts were enigmas until catalogs made them astrophysics. Each case taught the same lesson. A single odd event is a story. A replicable behavior is science. Decoding needs guardrails too. If a carrier hides cargo, resist the novelist's urge. Try simplest encodings, first primes, binary blocks, checksums, and publish failures as well as wins. Pre-register a decoding plan as labs pre-register clinical studies. Use cross-validation. Teach your algorithm on part of the data. Test it on the rest. If your method decodes ordinary noise into pictures, you have built a dream machine, not a decoder. None of this sands the romance off the search. The point is to guard wonder from wishful thinking. You can be moved by a hairline drift and still demand it pass the checklist. Awe and rigor are teammates. Rigor keeps awe from curdling into credulity. Awe keeps rigor from hardening into cynicism. Psychology is not confined to control rooms. When a candidate leaks, public hope becomes a force field. Rumors sprint, hoaxes bloom, deep-faked dashboards appear. The antidote is transparency and reproducibility. Post data in standard formats. Invite independent groups to try to break the claim. Speak in verbs and numbers, not metaphors. We saw a 1.2 Hz wide line drifting at 0.08 Hz per second. Present in beam 5 only, absent off target. Repeated on 3 nights, says much without saying too much. Design the human environment with as much care as the receiver. Short shifts. Quiet rooms. 2-person checks on parameter changes. A checklist taped beside every console that reads like an airline cockpit, because what you are trying not to crash is credibility. Teach bias on day 1. Play illusions. Let new listeners hear random audio that suggests words. Then show how integration beats illusion and how independent confirmation beats confidence. In the end, you cannot remove the human from the loop, and you should not try. What you can do is harness the human well. Curiosity supplies motive power. Discipline supplies steering. The nearest hello will be easy to imagine long before it is easy to prove. Build a culture where imagination is welcome and proof is mandatory, and you will be ready for both the thrill and the work. If this sounds like psychology in the service of engineering, that's exactly right. Telescopes listen with aluminum and silicon. Teams listen with nervous systems tuned by dreams and trained by habits. When a real whisper survives scrutiny, the system that recognizes it will be half hardware, half culture, and wholly prepared. Next, we pivot from minds to environment and follow our planet's radio. Whether the satellites, towers, and radars that fill our sky, and how a search for a nearby hello threads between them without getting lost. Call it radio weather. Above every city, a storm of signals blows day and night, cell towers chattering, aircraft talking to radar, satellites handing off data, Wi-Fi and Bluetooth whispering through walls. Even deserts have radio fences, military ranges, air traffic beacons, microwave links riding over the horizon. A search for a nearby hello must move through this weather without mistaking a gust for a greeting. Start at ground level. Towers paint the sky in narrow slices, each licensed for a purpose. Some bands are quiet by agreement. Astronomy has carved out sanctuaries where transmitters are restricted, but the edges leak. Modern receivers are exquisitely sensitive. What your phone ignores is background. A cryogenic amplifier treats like a shout. Good sites hide in valleys or wide plains far from cities. Terrain helps. Hills block low-angle noise, and long horizons mean you can spot interference coming by its geometry before it stains the data. Then there is the air above. Aircraft transponders ping. Weather and airport radars sweep. Navigation beacons tick. All have fingerprints, known frequencies, known cadences. Observatories keep live sky ledgers of local emitters and feed them into the pipeline. If a line matches a scheduled radar sweep to the second, it goes straight to the discard pile. Planes constantly update their positions. Cross-checking with public air traffic feeds lets software veto features that fly with an airplane rather than with a star. Space adds another layer. Satellites pass in strings and shells. They chat with ground stations, hand off to each other, and broadcast in well-defined lanes. Many are cooperative neighbors. Their operators publish orbits and spectrum plans. Even so, reflections, harmonics, and intermodulation can make ghosts where no transmitter was meant to be. That is why multi-beam receivers are priceless. If a tone splashes across every beam at once, you are hearing the sky's grid, not a point in space. If it lives in just one beam and tracks the sky, interest rises. The best defenses are boring. Start with hardware discipline, clean connectors, tight shielding, and low noise amplifiers cooled until thermal hiss falls. Add filters that notch out the worst offenders before the signal ever touches a digitizer. Calibrate obsessively measure your own system's quirks so they do not masquerade as physics. Keep clocks locked to stable standards so drift corrections are precise rather than creative. Software is the second shield. Modern searches carve the spectrum into microscopic channels and score each one by multiple tests: signal to noise, drift coherence, presence or absence in neighboring beams, repeatability on cycles. They subtract known satellite passes, erase lines sitting at exact power grid harmonics, and flag patterns that show up in every direction at once. They also learn locally. A site builds a living catalog of pests, factory controllers, elevator motors, faulty fences that come and go with weather and work shifts. Each new detection passes checks against that catalog before it earns human attention. Culture is the third shield. Teams write playbooks in plain language. If a candidate appears, the first move is never a press release. It is a checklist. Point away, point back, rotate, polarization, swap backends. Call a second dish in a different country. When possible, capture raw voltages so nothing subtle is lost. Publish methods long before a crisis so the public understands why a careful "probably not" is a victory, not a failure. The goal is not to avoid false alarms. It is to make them short and educational. Quiet zones help. Some countries set aside regions where transmitters are limited so observatories can hear the sky cleanly. You still cannot ban the atmosphere, airplanes, or satellites, but you can lower the floor of local noise so a faint hairline has a chance. Radio quietness is also exported to sea and to high plateaus where air is thin and dry. The more patient the search, the more a few decibels of silence multiply into hours saved and doubts reduced. There is an ultimate quiet zone, the far side of the moon. The lunar bulk blocks Earth's radio thunder. No cell towers, no aircraft, no bright satellite downlinks, just space. Engineers have long sketched arrays there, from low-frequency dipoles to mid-band dishes. The logistics are hard, but the physics is sublime. If a near neighbor ever speaks softly, a lunar ear would hear it with a clarity no valley on Earth can match. Threading through radio weather also means scheduling smartly. Search where nature is quietest. The water hole between hydrogen and hydroxyl lines is a favorite, and when the human sky is least busy. Night hours cut some traffic. Local holidays change patterns. Coordinate globally. A candidate that appears at 3:12 local time in one hemisphere and again at 17:12 in another with the same drift and the same sky position survives a very strong filter without drama. Optical searches face their own weather scintillation, moonlight, clouds, but the interference ecology is different. Lasers do not crowd the night the way radios crowd the air. A brief, repeating optical wink stands out against starlight in a way even crowded radio bands sometimes cannot. That is why many programs run in parallel. Radio for reach and energy efficiency, optical for clarity and clean backgrounds. None of this is glamorous, and that is exactly why it works. The romance of a first hello will always tempt us to believe. Procedures tame that temptation. A technician swapping a cable with a checklist in hand is as vital to discovery as a scientist reading a waterfall plot. When a tone finally survives the gauntlet, we want the world to know it beat a system designed to say no as long as possible, and only then, reluctantly, say yes. There is a hopeful moral inside all this caution. Our planet is loud, but order exists in the noise. Towers keep to lanes, radars keep to schedules, satellites keep to orbits. Patience and math can subtract the weather and reveal the sky. Somewhere beyond the local storm, a neighbor could be holding a tone steady, riding the slow dance of two worlds. We cannot quiet Earth for them. We can become excellent at listening through our own thunder. Next, we turn from defense to offense and design the nearest beacon from the sender's side. How a cautious, thrifty civilization might build a hello we could not miss. and why its choices would tell us as much about them as the message itself. Design the sender's side. Picture an engineer on a nearby world tasked with building a hello. A practical neighbor cannot miss and will not drain their grid or reveal more than they intend. The brief reads like engineering, not myth. Pick a band, choose an antenna, set a duty cycle, define a signature, and ship something that still works decades from now. They start with the band. The sensible home is the water hole, the quiet patch near the hydrogen and hydroxyl lines. A beacon slightly offset from 1,420 megahertz has two virtues. Listeners already watch there, and interstellar gas treats it kindly across a few light years. Too low and the medium blurs pulses. Too high and beams grow so needle-thin that pointing and clock stability become painful without adding much for short ranges. Next comes the beam. Power is expensive. Gain is cheap if you can build precise metal. A dish a few tens of meters across at gigahertz frequencies throws a pencil beam that wastes almost no energy on empty sky. Our neighbor does not carpet bomb the galaxy with watts. They compile a short target list stars in the Earth transit zone, nearby sun-like stars, close red dwarfs with known planets, and set fixed windows for each, tied to sidereal time so the pattern is easy to verify. Duty cycle is where thrift and kindness meet. 10 minutes per night per target is tiny but huge in detectability if the tone is narrow and the schedule stubborn. The beacon does not speak continuously, it taps. Tap means intentional, tap means repeatable. Tap lets us stack nights until a hairline grows undeniable. Modulation balances obvious and informative. The top layer is a pilot, a razor-thin carrier that stays on throughout the window. That pilot is the Find Me spine. Sitting symmetrically around it are faint calibration lines that let a listener measure Doppler drift and prove design. Under the pilot lives cargo at a glacial rate, using conservative phase or frequency steps that survive long coherence times. Frames open with redundancy and checksums so a receiver can tell when a whole page has arrived. Polarization can carry meaning without culture. The pilot might arrive circular and flip-handedness on a predictable schedule, encoding a simple binary while also telling the receiver how to orient their feed. Slow exact flips that track the sender's clock are a telltale of will. The first pages teach a tiny alphabet. Start with counts, then a rectangle of bits whose dimensions are a product of two primes, so there are two sensible ways to unfold it. Show simple geometry, a spectrum of the sender's star, then a map that triangulates location by the timings of bright pulsars. Numbers appear alongside pictures, so there is no single brittle path to meaning. Everything repeats for years, so latecomers do not miss the preface. Placement matters. Broadcasting from the home world is convenient and risky. A safer design parks the beacon in high orbit, at a Lagrange point, or on an airless moon. That keeps local noise low, grants near-continuous power, and decouples hello from home address. The choice itself tells us something. A city center transmitter says confidence or naivete. An off-planet outpost says caution. Power does not need to be heroic. Solar is steady over centuries for most stars. Radioisotope or compact fission bridges, eclipses, and dust seasons. The real challenge is uptime. Reliability wins. Components are derated. Clocks are disciplined by redundant masers. Health packets mixed into the frame let a listener watch the beacon age. If stability improves 1 year and sags the next, we learn about their maintenance culture long before we can read their poetry. A clever sender designs the discovery path. They scatter breadcrumbs. First, you see the pilot and the symmetric triplet. Next, you notice the window returns at the same sidereal minute each night. Then, if you recorded baseband, you find a whispering subcarrier with a checksum that lights when a full frame is captured. Each breadcrumb reduces cognitive load and makes independent confirmation easy. Ethics leak through engineering. A neighbor-respecting beacon avoids trampling protected natural lines. It does not imitate natural phenomena. It invites verification rather than demanding belief. It uses structures and schedules that make hoaxes hard and third-party checks easy. It speaks slowly enough to include societies with smaller instruments and newer budgets. Extreme caution might split the hello across media. While the radio pilot holds the channel, a synchronized optical wink arrives a nanosecond pulse burst at a prime cadence. Catching both is potent evidence of deliberation. Crossband redundancy also rides out weather. Clouds kill lasers but not radio. A noisy band spoils radio but not a photon counter under a clean sky. Even content order reveals priorities. Do they begin with maps and math, or with chemistry and climate records? Do they define units by fundamental constants rather than parochial inches and seconds? Do they timestamp frames against pulsars so the message dates itself without our calendars? A society that invests in error correction before ornament tells one story. A society that sings after the checklist tells another. Finally, they plan for a reply that may never come. The beacon is a gift to the future as much as a knock on the present's door. Schedules are archived so descendants can keep the promise cheaply. If storms or politics silence it for a season, it resumes at the same minute next year. That stubbornness is not just an engineering virtue. It is the core of the hello. It says, we meant to be found, we expected to be tested, and we built this to survive neglect. If we ever catch a beacon built this way, the nearest part will not only be distance, it will be temperament. We will hear neighbors who chose patience over spectacle, clarity over cleverness, and shared physics over private myth. Their first sentence will be a line in the noise. Everything after that will tell us who they decided to be when they sent it. Build the ear, and the neighborhood gets louder. The nearest hello may be a thin line that appears briefly. So the winner is not one monster dish, but a smart network. Many instruments, many bands, and many long nights stitched together so no whisper slips through the seams. Start with what already works. Green Bank in West Virginia listens inside a protected quiet zone with a 100-meter dish. Fast in Guizhou, 500 meters across, is so sensitive it hears pulsars others miss. Meerkat in South Africa braids dozens of dishes into one ear and can split itself into multiple beams, tiling the sky like a honeycomb. In Australia, Murriangit Parks keeps steady watch beneath a southern sky bright with the Milky Way. Add the Allen Telescope Array in California, built to patrol many frequencies at once. Together, they form a backbone that can revisit the closest suns again and again. Tomorrow's hardware pushes that backbone further. The square-kilometer array will knit thousands of antennas in South Africa and Western Australia into an instrument tuned for faint, narrow signals across huge bandwidths. A next-generation very large array aims to do the same trick at higher frequencies in North America. On the optical side, ultra-fast photon counters watch for nanosecond laser pulses from nearby suns. Projects like Laser Ceti and University Optical Ceti programs are deploying identical cameras at multiple sites so that a brief, repeating wink can be verified from more than one horizon. Coverage is not only geography, it is time. A thrifty beacon might tap for 10 minutes at the same sidereal minute each night. Miss the window and you wait a year to stack the same seasons. The fix is cadence. Build schedules like heartbeat charts. Alpha Centauri at dusk, Proxima at midnight, Barnard's star before dawn. Then roll that pattern every clear night for months. Commensal observing helps too. While a telescope maps a galaxy or times a pulsar, a second computer quietly skims the same data stream for unnatural, hair-thin lines that drift with orbital mechanics. Software is the quiet revolution. Modern backends carve spectra into microchannels, search thousands of drift rates, and integrate for hours without blinking. Machine learning now serves as a janitor more than a judge. It classifies local interference, flags air traffic and satellite fingerprints, and routes only the cleanest, strangest lines to human eyes. The watchword is transparency. When an algorithm promotes or rejects a candidate, it should leave a paper trail anyone can follow. Black boxes make good headlines and bad science. Readable steps make results that other teams can trust. Open data multiplies ears. When candidates and even raw voltages are posted in standard formats, high schools, amateurs, and small observatories can try to break or confirm them. The same culture that powered citizen science exoplanet and pulsar hunts applies here. If it takes minutes for a second dish to check a line, it should take hours, not months, for the community to cross-examine the evidence. A nearest hello would be a global puzzle. The solution should be public by design. The battlefield is cluttered, so shielding matters. Cryogenic low-noise amplifiers cool the receiver's own hiss. Band-stop filters notch out the worst local offenders before signals ever touch a digitizer. High dynamic range samplers keep strong junk from bleeding into the quiet lanes where a beacon would live. Clocks disciplined by hydrogen masers keep the frequency grid honest so integration does not smear the prize. These are not luxuries, they are rails that keep patients from slipping into self-deception. Strategy matters too. Valleys and radio-quiet zones on Earth buy a few extra decibels of peace. Oceans and high deserts buy a few more. Balloon and satellite platforms can float above much of the clutter and scan broad swaths quickly, handing targets to ground dishes for confirmation. The far side of the moon is the gold standard for radio silence. Even a modest array of simple dipoles there would sleep under perfect darkness during the long lunar night and wake to a sky free of Earth's thunder. If a close neighbor ever speaks softly, a lunar ear would hear it cleanly. Do not ignore the infrastructure never meant for this job, but perfect for it. NASA's Deep Space Network and ESA's STRAC send and receive exquisitely stable tones to Mars and beyond. When schedules permit, those same antennas can run on, off-on checks of a nearby candidate. Timing arrays that listen to millisecond pulsars for ripples in spacetime also build maps of terrestrial interference that technosignature searches can piggyback on. Every precise instrument is a potential witness if we share playbooks and write small adapters. Radio is only half the story. NASA, ESA, and others already analyze exoplanet atmospheres for water, oxygen, methane, and carbon dioxide. The same tools can watch for industrial oddities, chlorofluorocarbons, nitrogen oxides, or other out-of-equilibrium mixes that would be technosignatures rather than biosignatures. Those clues are subtle, but favor nearby worlds where photons are scarce and telescopes can stare a long time. Link the bands and confidence climbs. Imagine a razor-thin radio pilot that taps at a fixed sidereal minute while a synchronized optical wink arrives on a prime number cadence. Independent media, shared timing, and the clean drift of orbital mechanics are hard to fake and easy to check. In the near term, the key upgrade is posture. Keep a short list of priority suns and a short list of partner observatories. Keep an always-on coordination channel so at 2 a.m. call in West Virginia becomes a 10 a.m. check in Europe and a dusk confirmation in Australia. Keep a public ledger where nights, frequencies, and nulls are logged in plain sight. Add resilience. Mirror data on multiple continents. Train students across languages and write joint agreements so a shutdown in one place becomes a hiccup, not a blackout. A nearby hello will belong to everyone the moment it exists. Our system should behave that way before it arrives. Put this together and the picture sharpens. The ear we need is a braid, cold metal, warm software, open logs, and global habits. No single strand can catch a whisper every time. Twisted together, they can. The neighborhood is small by galactic standards. The physics is kind at short range, with instruments we already have and upgrades already planned. we could plausibly hear a disciplined 10-minute tap from a close star and check it across the world before sunrise. The path is not a leap. It is 1,000 ordinary steps taken by people who decided to keep listening together. The rehearsal becomes real. A thin line appears where no line should be. It is 2:11 UTC. At Greenbank, a fine tone sits in the quiet band near hydrogen, drifting at a steady rate. On, off, on, still there when the dish returns, gone when it steps aside. One beam holds it, others are blank. The drift looks like a transmitter on a spinning, orbiting world. The log stays plain: frequency, drift, width, polarization, timestamps. Across the Pacific, FAST slews off a pulsar program and listens. Minutes later, its waterfall shows the same hairline, the same drift, absent off target. Parks checks next and sees it too. 3 sites, 2 hemispheres, 1 tone stitched to the sky. Polarization flips behave as physics predicts. Raw voltages roll to disk. The schedule listed Alpha Centauri A as a priority. The Doppler curve draws a shallow S matching daily spin laid over the binary's dance. Software subtracts known satellites, aircraft, and local pests. Power grid harmonics are quiet. The satellite almanac shows no passes in that lane. On-off, on repeats. Hardware swaps proceed. Clocks check against masers. The line stays. By dawn and dusk across the network, a brief bulletin goes out. It says only what is true. A 1 Hz wide line near the hydrogen band, drifting at a rate consistent with an equatorial transmitter present on 3 telescopes, absent off target, repeating at the same sidereal minute. It lists frequencies, sky coordinates, durations, and links to baseband files. It says what was ruled out and what was not. It does not use the word "everyone is trying not to think." Independent teams pull the files and rerun the search with their own code. The line appears where the coordinates say it should. The same drift rate pops as the best fit. Folding minutes from multiple nights reveals a faint comb, little, symmetric bumps around the carrier, evenly spaced. They look like calibration marks. A central pilot with 2 equal side lines fits cleanly. Symmetry on purpose is a flourish nature rarely bothers with. Night 2 tightens everything. The window opens at the same sidereal minute. The pilot and sidelines return. A deeper look at the baseband reveals a whisper under the carrier, too slow to change the waterfall but coherent across the capture. Aligned and averaged, a checksum lights at the end of a repeated frame. The payload is glacial bits per second at best, but redundancy makes it robust. The first full, verified frame lands before sunrise. Decoding begins in humility. The team hunts for universals. The header starts with counts, then primes, then a small grid unfolding into a rectangle with prime sides. The rectangle holds a simple spectrum, peaks at hydrogen and hydroxyl, a smaller bump at oxygen. Units are tied to fundamental constants, not parochial clocks and rulers. A second frame repeats the spectrum with the same counts, teaching a tiny alphabet of numbers and ratios. Nothing assumes language. Everything assumes physics. On night 3, an optical team catches a synchronized wink. A nanosecond pulse burst at a prime cadence, arriving within seconds of the radio window's start. 2 sites see it. The color stays constant. Timing jitter is tiny. Crossband confirmation hardens the case without a press conference. The collaboration posts methods and files and announces a candidate with the confidence of people who know how to say probably. The world finds out anyway. Rumors sprint, hoax videos bloom. Some pundits call the frequency too convenient and the symmetry too clean. Skeptics download the voltages, rebuild the plots, and recover the same drills. On, off, on, 1 beam only. Repeat at the sidereal minute. Drift that fits orbital mechanics. Optical pulses on the same ticks. Within a day, amateurs pile up optical confirmations. For radio, professionals confirm the pilot and comb. After a week, the primer pages have repeated enough that cautious teams agree on the alphabet. A third frame contains a map drawn in pulsar timings anchored by a spectrum of the sender's star. It points to Alpha Centauri A's neighborhood. A fourth frame carries a clock tagged by those same pulsars, dating the message without our calendars. Under it all, the pilot keeps lock, as if the discovery path were part of the design. Behind the scenes, committees meet about what not to do. No one presses reply. The norm holds: verify, inform, share, coordinate. There is nothing a hasty transmission can add that patience cannot improve. A working group drafts a public note in plain language. It explains tests, repeats, confirmations, optical corroboration, nulls, and uncertainties. It says what the pages show and what they do not. It does not pretend to know motive. Meanwhile, the practical work expands. More telescopes join. Observers sweep above and below the pilot for faint companions. They search adjacent nights in case a second window exists. They test for polarization flips on a longer cadence. They hunt for a slow message that may take days to repeat. The nearest hello becomes routine, and that is the strangest change. The line that felt miraculous on night one is now something the world can check on a schedule. Distance becomes a calendar. 4+ light years are a human wait. Even without a reply, the pilot is a conversation of a kind. It says we share physics. It says we planned for patience. It says we built this to be found by ears like yours. For a species that told campfire stories about voices in the dark, the miracle is not the line. It is the checklist, the cold amplifiers, the open files, and the decision to treat wonder like measurement. Nearness, in the end, is mercy. The beam is tight, the drift clean, the medium kind, the cadence human. We imagined first contact as spectacle. The closest version is steadier and truer, a narrow, stubborn spine that returns night after night until even a skeptic must call it real. Once you have a spine, you can grow a body. Once you have a hello, you can learn a language. The primer repeats like a tide. Each pass boosts confidence. Each repetition invites bolder questions. The opening header is mapped by consensus, counts, primes, a compact grid, then a spectrum that anchors units in physics rather than culture. Ratios define the yardstick. Periods define the clock. The design assumes a cautious neighbor and rewards patience. The second layer is structure, not poetry. Bits gather into rectangles whose dimensions are the product of two primes, inviting exactly two sensible ways to unfold them. Unfold them wrong and the picture dissolves. Unfold them right, and graphs appear that read like laboratory notes. A stellar spectrum, a curve for a planet's orbit, a small glyph marking inclination. Redundancy is generous. Multiple frames teach the same idea with slightly different scaffolding, so no single error can mislead you. A rhythm appears. Every nth frame is a page zero, a reset that redefines units by the same constants, making later pages self-sufficient even if they are all you ever catch. Checksums light at the edges like stitches on cloth, confirming that nothing is lost or duplicated. The payload crawls, but it is honest. No one is trying to dazzle. They are trying to be understood by an ear they have not met. A sketch of the sender takes shape. The stellar spectrum and pulsar timings point to the neighborhood of Alpha Centauri A. A small orbital diagram repeats, its scale expressed in units tied to hydrogen rather than inches or seconds. The diagram shows a world well inside the distance between A and B, with an orbital period equivalent to a few of our weeks. That does not guarantee habitability. It does guarantee intention. One page is a calibration rather than a map. Under the pilot tone sits a comb of faint lines at exact, stable intervals. Plot the sequence, and you get a chirp. Frequency against absolute time. Recreate the chirp and sweep a receiver across it, and your local clock and theirs momentarily share a heartbeat. Two laboratories under different suns synchronize within a sliver of a second using nothing but patience and hydrogen's number. Linguists, mathematicians, radio engineers, and data recovery experts form an instant commons. Teams build independent decoders and compare notes in public. They argue about rectangle layouts, about whether a run of bits is a symbol or a checksum, about whether a spike is a glyph or a calibration artifact. The arguments are not noise, they are quality control. When three codes extract the same orbit curve from different raw files, confidence climbs without speeches. Caution keeps exotic interpretations at bay. A rectangle that some swear is a planet's limb becomes, under stricter statistics, a phase diagram that tracks a repeating wink in the pilot, most likely a polarization flip used to mark block starts. Dreams give way to measurements, and the message remains beautiful without metaphors. The next milestone is a dictionary of the smallest possible words. The community agrees that certain bit patterns tag numbers, others tag units, and a few tag operations like add, repeat, and next. With those pebbles in hand, more ambitious pages become legible. One shows a compact table of elemental lines: hydrogen, helium, oxygen, nitrogen, sodium, annotated with ratios. Another shows a skewed ellipse whose captions decouple mass, radius, and period. Motive stays invisible, and that absence is instructive. We are not reading a manifesto. We are reading front matter for a manual. The nearest hello, so far, is a scaffolding of shared measurement. It assumes the listener will build insight once clocks align and units match. It treats comprehension as a joint project rather than a show. Outside the labs, the world tries to sprint faster than evidence can carry it. Some corners cry hoax because the pattern is neat. Others insist the third page promises medicine or salvation. Reputable outlets mostly do better. Because the data are public, anyone can download the files and see the pilot and the comb and the checksums. Anyone can reproduce the on-off, on tests and the sidereal timing. Truth, this time, is not a press release. It is a reproducible habit. Schools write lesson plans overnight. A middle school class in Nairobi runs a simplified decoder and recovers the prime run. A group in Sao Paulo repeats the polarization test with a small dish borrowed from a university. A ham radio club in Poland uses an optical photometer on a homemade telescope to time the nanosecond pulses and confirm the cadence. The first hello becomes a shared lab, not a distant rumor. Curiosity turns into measurable skill. As the primer hardens, a question grows louder. Is there anything beyond it? If this is only the table of contents, what is Chapter 1? The slow subcarrier hints that more hides in the carrier's phase, but teasing it out demands weeks of clean captures and long integrations. The community chooses patience. It is easier to lose a message than to decode it twice. Schedules are drawn for a month of nightly windows, and the criteria for claiming a new pattern are published before the first night begins. Even restraint glows with wonder. Synchronizing clocks across 4 light years with a comb under a carrier is not a headline writer's dream, but it is a civilization's dream. It means comparison experiments are now possible. A neutrino detector can be told when to look for a burst. A small optical array can be told when to expect a wink. 2 laboratories that evolved under different suns just shook hands. The primer, then, is not small. It is the bridge that makes larger meaning possible without argument. It is also the purest expression of nearness. A beacon this modest would blur across hundreds of light years. At 4, it arrives tidy enough for a cautious species to learn it in public. The nearest hello is teaching us how to agree on what we see before we ask what it means. That alone is a revolution. The debate arrives as gently as the signal did, around kitchen tables and in parliament halls, under dorm lights and in quiet labs. The question takes a simple shape. Do we answer? The pilot keeps tapping. The optical wink stays punctual, and every night, the primer resets our shared yardsticks. The message is not a story. It is a handshake. A handshake invites a reply. Caution has seniority. For decades, scientists drafted post-detection norms that say, verify first, publish widely, and do not transmit on behalf of Earth without international consultation. The reasons are not melodramatic. They are practical. A rushed answer cannot add anything. A patient one will not improve. A loud answer could drown out the listening we still need to do. The nearest hello gives us a rare luxury. Time measured in years, clarity measured in repeats. No one needs to sprint. Still, the human urge to speak is strong. Children write hello on poster board and hold it up to the sky. Musicians talk about a chord that would translate into numbers. Poets sigh. Engineers reach for whiteboards. If a reply ever goes, it will be born in the quiet space between those impulses, where care and curiosity share a bench. Start with what we know. The sender values thrift, clarity, and verifiability. They taught units before nouns. They synchronized clocks before songs. If we respect their design, a first reply would mirror that philosophy. Not a manifesto, not a broadcast in every direction, not an all-day shout. A narrow, patient tap at a predictable sidereal minute, placed in the band where we found them, using a pilot tone with simple side marks that echo theirs. The content would be minimal and universal. Counts, primes, the same constants. A small rectangle that unfolds into a spectrum of our star, and a map drawn in pulsar timings pointing back to us. In other words, we would return the handshake. Even that is not step one. Listening is step one. Before any reply, the community wants to know whether Chapter 1 exists behind the primer. Schedules are made for a month of nightly windows. Teams agree on what will count as a new layer. A repeatable pattern under the carrier, a second optical cadence, a rare polarization flip that encodes timing marks, a frame that differs in a way redundancy predicts. The criteria are public so that when claims arrive, the world can measure them against promises rather than against hope. Governance grows teeth in the meantime. The conversation expands from labs to law. International bodies that handle space treaties and frequency rights convene working groups. The questions are not philosophical abstractions. They are logistics. Who aims a transmitter? Who funds power and hardware? Who manages time on dishes that also run weather and deep space missions? Who writes the text of a reply, and who signs off? The answer that keeps winning is modest. No single nation, no single observatory, no single lab. A coalition with public minutes and a narrow mandate to draft a reversible, low-power, testable reply plan that does not curtail listening. The plan, as it evolves, looks like this. Phase 1. Simulation only. Build the reply encoder. Test it on a spacecraft carrier in deep space, and let independent teams try to decode it blind. Phase 2. Rehearsal against a star that is not the target. Aim the transmitter far from Alpha Centauri and confirm that no bleed appears in the target band. Phase 3. A silent rehearsal pointing and timing without power to confirm schedules and handoffs across continents. Only after those passes would any power be committed, and even then, only during a tiny window, and only at a level that will be unmistakable to a nearby, prepared ear but invisible elsewhere. Content remains the hardest problem, because content leaks priorities. We could talk about our atmosphere and orbital period, our clock, and our unit choices. We could add a map of pulsars that matches theirs. We could include a small table of elemental lines with ratios. We could mirror their comb and chirp so clocks lock. Beyond that, everything feels loud. A drawing of our surface begs interpretation we cannot control. A list of our molecules invites politics we cannot represent. The draft reply everyone can live with simply teaches how to align clocks and decode frames, declares the sender and receiver by pulsar map, and leaves a space where a future page could be placed after further debate. While committees draft carefully, Culture hums. Museums mount exhibits where visitors can scroll through waterfall plots and watch the pilot's hairline drift in real time. Schools run labs where students fold the same prime rectangles the professionals do. Amateur optical teams coordinate winks from backyards and mountaintops. Faith leaders preach patience. Philosophers write essays that do not insist on answers. The first hello is not a sermon or a scare. It is a lab assignment the whole species can join. Some fear fades, and some fear grows. The fear that a reply will summon harm loses air as the months pass, and the beacon keeps behaving like a lab instrument rather than a trap. The fear that we will divide into shouting camps gains air and is met, not with rebukes, but with process. Public comment windows open for reply drafts. Translators render technical notes into dozens of languages. Critics are invited to propose safer schedules, smaller powers, narrower frames. When they do, the plan improves. A once-in-a-century event becomes the most boring kind of public work, iterative and documented. Quietly, the message itself deepens. A tiny modulation under the pilot repeats on the 11th night at a phase the primer predicted. Stacked across weeks, it forms a short block that compresses without loss, as if designed to be robust against our worst weather and their occasional maintenance. It teaches a second glyph set that tags operations add, subtract, next, then it stops. It is enough to let decoders agree on arithmetic without touching culture. It is an invitation to move beyond calibration, but not an insistence. There is a temptation to read motive into restraint. Maybe they are cautious because they fear eavesdroppers. Maybe they believe ethics require consent before content. Maybe they learned the hard way that early chapters should be tutorials, not epics. Or maybe they are like us, a patchwork of labs and budgets, of traditions and protocols, doing the most they can do without presuming to speak for everyone. The nearest hello feels less like a proclamation from a single voice and more like the patient work of a committee that learned to design for strangers. A year passes by the calendar. A handful of minutes pass by the beacon. Nothing breaks. Nothing accelerates. The pilot taps. The optical wink returns. The primer stitches frames together, and the subcarrier drips a second math. The world, astonishingly, adapts. The thrill does not vanish. It becomes a habit. The nearest hello is no longer a headline but a metronome. It marks time for a species learning to be methodical under wonder. If a reply goes someday, it will feel less like fireworks and more like a lab note slipped across a bench. Here is our clock. Here is our star. Here are the constants we share. Here is the way to unfold the frame. It will be small enough that almost no one hears it by accident, modest enough that it does not set policy by surprise, and clear enough that the neighbors who taught us patience will know we listened well. Nearness gave us that luxury. A whisper from 4 light years away rewards restraint because it survives restraint. We do not have to shout to be heard, and we do not have to rush to be honest. The first hello is teaching us how to be the kind of listeners worth answering. Whether we speak next or not, that lesson may be the most valuable message in the whole exchange. Endings in science are rarely endings. They are handoffs from one question to the next, from one generation's tools to the next generation's hands. Our story began with a hiss of static and a phantom word that seemed to bloom out of the noise. It grew into a neighborhood map of nearby suns, into the practical math of narrow beams and quiet bands, into checklists, habits, and the courage to say probably not until probably could stand. It carried us through psychology and radio weather, through the design of a thrifty beacon and the braid of ears that might hear it. And then, one night, the line appeared where no line should be and kept its promise with a patience that matched our own. What changed after that was not simply that we believed. It was that belief became a reproducible behavior. A tone was there when we pointed and gone when we stepped aside. A drift fit the dance of orbits. An optical wink landed on the same ticks. Files were posted in the open. Students and amateurs repeated the plots. The first pages of a primer unfolded into shared clocks and shared units. The hello did not arrive as a speech. It arrived as a way of working together. If this is where the credits rolled, what would we say we learned? First, that nearness is mercy. Physics is kinder at short range. A narrow line stays tidy. A patient schedule pays off within a human lifetime. The difference between 4 light years and 4,000 is not just distance. It is whether a careful species can verify what it loves. Second, that awe and rigor are teammates. Wonder keeps us listening. Rigor keeps us honest. Third, that openness is the superpower of small civilizations. Publishing methods and data turns rumor into homework and homework into consensus. The nearest hello did not belong to any single nation or lab. It never could. It belonged to anyone with curiosity and the willingness to read a waterfall plot. We also learned what not to do. We do not sprint when time is on our side. We do not crash listening by shouting over it. We do not confuse spectacle with substance. The beacon's design taught the same lesson. It spoke in measurement before meaning, in calibration before culture. It taught us to synchronize clocks across 4 light years and to unfold rectangles by prime factors, to anchor units in constants instead of customs. It showed us that the path to understanding begins with a shared ruler and a shared second. There is a quieter lesson, too. The nearest hello made us look at ourselves. We built procedures to tame bias because we wanted to deserve what we might find. We trained our rooms to be boring at 2 a.m. because credibility is built in boring rooms. We taught students to love null results because every no sharpened the ear that would one day hear yes. We discovered that a civilization is not the sum of its inventions. It is the sum of its habits when the world is watching. What comes next may be dramatic or modest. The primer may hide a chapter 1 that teaches arithmetic without words and then pauses, inviting us to decide who speaks for us. Or perhaps the first pages are the whole book for now, a standing wave of goodwill that binds 2 laboratories by shared timing and leaves the rest to future hands. Either way, the important change has already happened. The line that felt miraculous on night 1 now lives on a schedule, and millions of us know how to check it. We can disagree without losing the plot because we can reread the raw voltages together. Whatever follows will not be a rumor that only a few can touch. It will be a measurement anyone can learn to see. If no further layers ever arrive, nothing breaks. We will have synchronized clocks with a neighbor and proved we are capable of patience under wonder. The search will not stop. It will expand in the ways we now understand matter. More nights, cleaner sites, wider bands, smarter software, and public ledgers that make probably not a badge of honor instead of a bruise. The habits we forged for a nearby whisper will make us better listeners for everything else, the chemistry of young worlds, the lonely thumps of distant pulsars, the faint fingerprints of life in a thin atmosphere far away. And if chapter 1 does arrive, if a slow, robust layer teaches numbers, then geometry, then a map that points from their star to ours with a pulsar clock in the corner, then the calendar will gain a quiet holiday, not a day of triumph, a day of maintenance. A day where we re-level the instruments, renew the agreements, update the open notebooks, and remind ourselves that we are stewards of a library we did not build alone. A day where we acknowledge that the most human thing in the whole exchange was not the thrill. It was the discipline that made the thrill real. When we began, we asked how far a whisper can travel. The answer is farther than pride, faster than rumor, and deep enough to make patience a virtue you can graph. A whisper crossed 4 light years because 2 sets of engineers, under different suns, agreed that shared physics is a language worth speaking. A whisper became a handshake because 2 sets of listeners agreed that the only way to honor wonder is to measure it in public. The romance did not fade under the math. It grew up inside it. Midnight again. The hiss returns, and with it the same thin word your brain is prepared to hear. This time, the pause that follows is not fear or doubt, it is respect. We are not alone in the way a child imagines. We are not alone in the way a laboratory proves. Somewhere, a pencil-thin beam rides a quiet lane at the edge of hydrogen and asks a neighbor to meet it halfway. We met it, not with trumpets, but with clocks. Hello, is anyone there? We do not answer with a shout. We answer with a posture. We keep the schedule. We keep the files open. We keep the ears cold and the logs plain. We build the kind of civilization that a nearby hello imagines on the other end of the line. If the next page arrives, we will read it together. If it does not, we will keep the promise anyway. From mos plus as ad to a. We are here. We are listening. We are ready for whatever the nearest silence becomes.